Okay, good morning. Last week we stopped in the first chapter, or in the third chapter of data. And maybe I should decrease the sound a little bit. We stopped in the chapter of data analysis, data in general, at slide 23, if I remember correctly. So we didn't yet get to explaining box plots. Am I correct with that? Okay. First question, are there any questions regarding the rest of the data chapter? Okay, right. Then let's get to our first visualization technique. Because last week we talked about central tendencies, so we talked about how a data set might be more on the positive side, more on the negative side of things, but there are specific visualization techniques to show the tendencies, the dispersion of data in a data set, in a numerical data set, to be specific, a lot better. To do that, we first need some terms. One term is range of data. Range of data is pretty simple. It's just the difference between the lowest, the smallest value, and the highest value. So, range of data. So, if a data range, we have four values, 1, 5, 6, and 7, then the range would be 6 because we have the difference between 1 and 7. It's a pretty simple value. A little bit more complicated are the quartiles. The quartiles are simply, we already know one quartile. We already know the median. The median is the second quartile because it's right in the middle, the value right in the middle. And instead of splitting our values it's not good. Only right in the middle, so only talking about the median. We can also talk about the first quartile and the third quartile. So we split it even more. So the 25th percentile and the 75th percentile are the first and the third quartile. They are pretty similar to the median. They are basically calculated the same way. If we are in between two values, we also have to use the average value between the two values in between. It's in between. Based on the quartile, we can also define this so-called interquartile range. Interquartile range is something we will also discuss in the last chapter of the semester, the outlier detection, because it's often used to define outliers. The most simple way to define outliers is to take a look at the interquartile range. So this range, and take a look at values that are above or below this range in a certain percentage. So most often outliers are defined as 1.5 or 2.5 times interquartile range above or below the first and third quartile. We will see how that looks in a second once we take a look at the box plot for the first time. These terms are now very important to get to a box plot, because a box plot is basically a visualization of these values. In a box plot, we first take a look at the first quartile. So the value where 25% of values are below. This defines the line, the left line of the box plot. Then we take a look at the median. That's the middle line of the box plot. We can also we also have to take a look at the third quartile because it's the upper end of the box. And now we only have this blue box in here. But a box plot contains more values. To draw these lines here, ended by little lines called whiskers, we have to take a look at the lowest value that isn't an outlier. So to be able to draw this line down here, we have to first define what outliers are. And that's something we can do with the interquartile range. So if we are, for example, using the 1.5 times interquartile range definition, then we first have to take a look at which values are below the first quartile more than 1.5 times interquartile range. In this example, since we have the first quartile at 2 and the third quartile at 5.5, the interquartile range is 3.5. So if we take this interquartile range and let's, for the sake of simplicity, use 2 times interquartile range and not 1.5 times. So 2 times interquartile range would be 7 in this case. Then every value below -5 would be an outlier by this definition. Because we take a look at 2 as the first quartile, subtract 7 from that, and everything below that is defined as an outlier. So in this case, we do not have any outliers. And the same is, of course, done here, where outliers start at 12, because third quartile plus 7. We also do not have this. So we do not have any outliers. And we know that our whiskers, so the outside, the small lines in here in the box plot, would lie at 1 for the lowest value that isn't an outlier, and would lie at 7 for the upper whiskers in here. Okay? If we would replace this one with a 13, the quartiles would stay the same, because quartiles are not sensitive to outliers. Then, of course, the upper whiskers would lay at 6, and the 13 would become an outlier, and this outlier would be displayed as a little circle at the point of 13. So probably around here, there would be a little circle displaying this outlier. We see that in another example in a second. Okay? The principle of box plots is hopefully understandable. Okay? These box plots are often used to display a lot of different compositions of data against each other. So we can, for example, use that to display the average daily temperature per month. In this case, we are talking about the average temperature in Nuremberg for a certain range of years. And we can see that, of course, in January and December, the temperatures are the lowest in general, because we can see that the box itself is pretty low compared to for example, July. But we can also see that there are some outliers to the lower end in January and December while in July the outliers tend to be hotter than the other temperatures. And we can read a lot out of box plots. We can read a lot out of comparing box plots of different scenarios, because we see a lot of information in here. However, box plots are pretty static and do not really display the distribution. We can have, for example, two hills to the side, so we can have a distribution like this and a distribution like this might lead to the same box plot. That's something we can see in a box plot. That's the reason why we need also other visualization techniques. Other visualization technique for basic statistical descriptions that is often used is, for example, a histogram. A histogram is also something we will see a lot during the semester. We can also use a quantile plot, something I will explain in a second, which can be extended to a quantile plot, and we can also use a scatter plot. Let's first start with a histogram. A histogram is better in displaying things like this, because we can show distributions. A histogram simply puts values of a certain range into one bucket. For example, we can, if you're using the same thing as here, say, hey, we want a histogram with equal width buckets, where we put values from 1 to 4 in a bucket, 1 to 5 to 8 in a bucket, 8 to 9 to 12 in a bucket, and then let's use 12 in here, and we have a histogram with 3 buckets. Then we would simply count how many values are in the first bucket. Well, we have 5 values in the first bucket. We have 1 value in the second bucket and 1 value in the third bucket. And therefore, we would end up with a histogram like this, where we have the first bucket, the second bucket, the third bucket, and simply have the amount of values that are in each bucket. So we have 5 values in the first bucket, 1 value in the second bucket, 1 value in the third bucket. And that's a histogram, basically. Okay? Hopefully that's big enough for the recording. However, I think it might. Pretty simple to use. We can, of course, then also smoothen that with a graph. Most often that's not done, but we might do that if necessary. There are also different types of defining bins. We can have equal width and equal height definitions. For histograms, we most often use equal width. So the buckets are defined as a certain width and have the same width for every bucket. Sometimes, and that's more often used in other techniques, we also have equal height definitions, where we define that the value of values, the amount of values in each bucket should be the same. That wouldn't make really sense for histogram in most cases. So most often we are using equal width definitions in here. The good thing is that, as I said here already, histograms tell us a lot more than box plots in many cases. Depending on the amount of buckets we are using, of course. If we are using a low amount of buckets, we are losing a lot of information. If you're using a higher amount of buckets, then the histogram might be harder to read, of course. However, we can differentiate between distributions like this and this in histograms. Histograms, yes. We couldn't do that in box plots. They are two different tools with different strengths. And most often they are used together because we can also tell things from a box plot which we can't tell from a histogram. Do you know examples for things we can't tell from histogram but can tell from a box plot? So checking whether you are all sleeping or awake right now. Any ideas? What can I read from a box plot which I can't read from a histogram? Because if a histogram cannot tell us everything a box plot can tell us, why should we have to use a box plot? Sorry? The median? Yeah, we can only guesstimate a rough estimate in here, yeah? Median, for example. Outliers is a very big point. We can't see outliers in here. Typically, a histogram either is pre-stripped of all outliers, or it contains just very low bars at the side. But we can't specifically read outliers out of a histogram. That's not possible. Yeah, and of course we can't see the exact values for Q1 and Q3. That's pretty similar to the median, so I wouldn't do that extra. Okay, so specific values are easier to read out of box plots, but histograms tell us more about the distribution, how the distribution is created. Next thing, and that's something where we first have to define a new term. We already know about quartiles. So we know about 25%, 50%, 75%. Next to quartiles, we also have quantiles. Quantiles are related. While quartiles are only at the 25th at each quarter, quantiles can be at every percentage. So we can define a 25% quantile, for example. We can define a 25% quantile, which is exactly the same as the first quartile, because it lies at 25% of data. So if we define a quantile at 1%, it means that 1% of data has to lie below this value. And we can define a quantile for every percentage we want. If we can define a quantile for every percentage we want, we can of course also see at which value we reach a certain threshold. So in this quantile plot, we can read now that, let's say this is at $0.1 in here for the y-axis. Then we can see that at, let's go here, that's easier. The 20% quantile, Q value, says us that 20% of unit prices are below, let's say, $4.34. So 20% of values are at a price below $3. Of course, it's hard to read out of a diagram exactly. Normally, you would have some interactive tool to see exactly where the quantile lies. But a quantile plot simply shows us how many or which percentage of values is below a certain unit price in this case. Which can be also important for a case like this, where we want to know about prices. It tells us also a lot about distribution. There might be a certain bump in something like this. That's also possible. Most often it's more or less exponential because we add up things. We can also compare two different distributions against each other using a quantile to quantile plot, where we simply take a quantile plot of one branch and compare it to the quantile plot of another branch. Out of something like this, we gain the information how these two compare to each other. In this case, we see that the line of the branch 1 is certainly below the line of branch 2. So in branch 2, we get to 200 a lot faster than with branch 1. And therefore, we know that the unit prices of items sold at branch 1 tend to be lower than those that are sold at branch 2, which is also a useful information to know about. And last but not least, we can also take a look at scatter plots. Scatter plots, again, compare two different sources of data, most often, if it's a two-dimensional scatter plot, which is the only thing we can really comprehend as a human, where we draw the values out of two different dimensions against each other. So let's say we have a data set with two dimensions, so A and B, and these have the values 1, 2, 2, 1, 3, 3. Then a scatter plot is pretty simple to draw. Of course, in real world we would have a lot more information, something like this. Then we would have one dimension for B and one dimension for A. 1, 2, 3, 1, 2, 3. If you draw the first point, it's at 1 and 2, so here. Then we have 1 point here, and we have 1 point here. If you draw that for a bigger data set, we end up with a bigger scatter plot, like here, and we can also see some, I'm using this word because although we do not yet talk about it, clusters of data. So we will use scatter plots, for example, in clustering a lot, which is the latest chapter of a semester. But you see a lot of clusters also visually, so you see that we have a big cluster of data, for example, in the second scatter plot here, which doesn't cluster with the data down here. But that's something for a later lecture. But scatter plots are also nice to see distributions of two different dimensions against each other. One important, we will do that at a later point as well. Scatter plots can also be used for correlation analysis. Maybe we get to that today. I don't think so, but we will see that later. Okay, those are the most basic visualization techniques we can talk about now. We will talk about some more advanced visualization techniques in a second. But before that, we have to first talk about data profiling. Because data profiling is basically the thing we have to do with data. We want to collect data about data, to compute the median, to compute the mean, to compute the variance, to compute the quartiles. That's all collecting data about data. We're collecting metadata about our data set. And that's very useful for us to do as a first step in a data science project. Because we can find frequent values, we can find distributions, we can find things like that. And we can gain some feeling for our data set. And basically, that's what we have done in this lecture, and you are doing this week in the exercises as well. That's about data profiling. So if somebody is using the word data profiling, you should know that's data profiling. Okay? With that out of the picture, we can get to data visualization, to more advanced data visualization techniques. Due to the fact that we are already behind in our schedule a little bit, which is not bad, but still, we go through that in a lot of speed because the exercises contain examples, better examples for every visualization technique. I still want to know you to get to know the different categories of data visualization. First, why do we want to visualize data? Well, we want to gain insight into our data. By visualizing data, we get a better feeling for the data. We can transport information via visualization. Most often, if you are a business analyst, you would present your results in visualization techniques to your bosses because they can comprehend data a lot better via visualized data than via written data. If I simply write down the median, the first quartile, the second quartile, and the viscous, it's far worse to comprehend than if I draw a box plot, for example. For more advanced techniques like this, it's even more relevant that it's easier to comprehend. Of course, they provide an overview. Visualizations always provide an overview over data. And they can show us patterns, trends easily. And often they also provide some kind of visual proof because we can easier comprehend the thing, which is nice. For KDD, we divide visualization techniques, advanced visualization techniques, into 5 categories. And we will talk about 1 or 2 examples for each of these in here. We can talk about pixel-oriented visualization techniques, geometric visualization techniques, icon-based visualization techniques, hierarchical visualization techniques, and more complex data visualization techniques, which is basically all other things. Let's first start with pixel-oriented visualization techniques. For these, the most common methods are circle segment diagrams and heat maps. Heat maps are the more common used technique, so we will just show a heat map in here. Basically, pixel-oriented visualization techniques are simply based on pixels. So we use a pixel to display some kind of density or things like that. For heat maps, we simply can take a look at some heat maps. We are using really every pixel is displaying a certain bucket, and we draw it in a different density or color to display how many entries are in this pixel bucket. For age, that's a good example. We see maybe we maybe define the first top left pixel as H1, then H2, then H3, and so on. And the darker a pixel gets, the more persons lie in this bucket. It's pretty simple to understand. We can do the same for income. In this case, it's more about a line is defined as a pixel. That's also fine. A heat map doesn't have to have single pixels. It can also be a line. And we see that the lower incomes down here have more values in them than the higher incomes up here, which is pretty normal. For credit limit, there are more persons with a lower credit limit than persons with a higher credit limit. Same thing. And transaction volume, in this case, it's more dense in the middle because there are less transactions with 1 cent, 2 cents, whatever. There may be more with 50 euros, and there are less with 200,000 euros, of course. So it's pretty easy to read, and can also be shown in colors, of course. We can also color code it. Sometimes it's just darkness, so intensity. It's often also color coded. But it's about showing basically a histogram in a more sophisticated way, because we simply extend that a little bit in a two-dimensional space. You will see these things often in first analysis of numerical data, but also in categorical data. That's the big advantage compared to histograms. Both are only possible with numerical data. Histograms can be also used with categorical data, a heat map, sorry. Next thing, geometric visualizations, sorry. In geometric visualizations, we can also put scatter plots and scatter plot matrices into that. We can also talk about polar plots. There are some other methods like parallel coordinates, projection pursuit, projection fuse, and hyperslice, which we will not take a look at in KDD. However, these are also part of the geometric visualizations. For scatter plots, I also already explained how they work in general, but we can also put a lot of scatter plots into a scatter plot matrix. Because in a scatter plot, we can only compare 2 dimensions with each other. If we want to compare more than 2 dimensions, we have to use more scatter plots to do that. So if we have a data set with dimensions A, B, C, we would draw a matrix where we draw every dimension in here. If we are comparing A to A, of course, we would just get a line in here, because it's perfectly correlated. So in this case, we would use some kind of other diagram. Most often we would use a histogram or things like that. But basically, this is not defined, this is not defined, and this is not defined. We can use every kind of diagram we want. For all of all other diagrams, we would use we would draw a diagram, a scatter plot diagram, where we compare A to B in here, where we compare A to C in here in a scatter plot. We would compare B to C in here, B to A in here, and so on and so on. So basically, we would draw a scatter plot for every comparison. You might also see that, of course, we have some duplicates in here. These two diagrams, for example, this diagram up here and this diagram down here, is just turned around. Because we are still comparing the same values against each other, just with turned around axes. But that's something, if you do that automatically, it's not a big problem to do. Scatterplot matrices are pretty good if you want to gain some insights about the distributions in a whole multi-dimensional data set, where you would draw a scatterplot for each comparison. You can simply use a scatterplot matrix. Polar plots are also useful to compare different dimensions of a data set. And they are especially good if we have multi-dimensions. A polar plot, again, uses, for example, the dimensions A, B, C, with values 1, 1, 1, whatever. Then in a polar plot, we would have one direction, one angle for A. We would have one angle for B and one angle for C. For all of the dimensions, we have an angle. And depending on the values, we have a scale in here for every value. We can now draw the values of this tuple. If we have a second tuple, 3, 2, 4, we can also draw that into that. I do not have colored things in here, but hopefully it's enough if I draw this. 2, 3, 4. So that's a polar plot for this simple data set. It's nice to compare single entities, data entries. However, a polar plot has a big disadvantage. If you have a lot of tuples, it gets too hard to read. These polar plots, and that's something that's simply due to the fact that a lot of you are IT guys and data science guys. A lot of you might have played Pokemon in the past. And Pokemon is using these polar plots, for example, to show internal values of Pokemons. So it's already in the game. So you might have seen that as a five-year-old child for the first time, because it's pretty easy to comprehend. But big downside, it gets crowded with too much data records, of course. Next thing is icon-based visualization. Icon-based visualization is something that is most often used to just show data to persons that do not like seeing numbers, I would say. Because in icon-based visualization, we simplify data, which would be far more detailed if we would take a look at numbers, but it simplifies it and therefore is easier to comprehend. Especially stick figures. We have something like Chernoff phases, which I threw out of the lecture because it's not so relevant for KDD, but those are also icon-based visualization, and we can have shape coding, color icons, tile bars. The simplest and most easy to comprehend thing is stick figures, where we simply have an icon-based diagram displaying how many entries are in a certain category of data. So for this example, we are taking a look at the number of students at FAU at every faculty. So we have 5 faculties, and we can easily comprehend that most students are within the Faculty of Engineering, second most are in the Business, Economics and Law faculty, and then it gets lower to Faculty of Sciences, Faculty of Medicine, and Faculty of Humanities is also here. It's pretty easy to comprehend. However, we are losing information about the details because it's rounded to a figure. We will not draw a half figure in here. We can also use that for genders, for example. We can use that for every kind of categorization of a data set. And it's often done to visualize things like this. So I know that FAU used a figure like this to display the distribution of students in their official prospect. Yeah. I wouldn't say it's that useful if you're really doing data science to gain insights on the data, where you would most often use another method of doing things, because it's more precise. But if you're a business analyst and want to show your results, then it's pretty easy, pretty nice. Next thing is hierarchical visualization. Where we will take a look at tree maps. There are also three-dimensional cone trees. Three-dimensionality in visualization is also often more complex, so I skipped that. But tree maps are very useful because they are splitting, or they are basically doing the same thing we have done with stick figures. Where we are splitting the 100% rectangle into different sections, where we draw how many sections are, how many students are in each faculty. The good thing, and that's the hierarchical path of that, is we can have a tree map where we have maybe 3 rectangles, so we have maybe, let's say 60%, 20%, and 20% at one level. But we can split these rectangles up even more. So in a dynamic analysis, we can now say, hey, let's split up the technical faculty into different departments. So this 60% rectangle might contain some smaller rectangles to display a lower level of hierarchy. And we can even split that up even more and even more, because it's working the same way. We have a 100% rectangle, which we can split up according to the distribution. So a tree map is a more useful, useful is not that good of a word in here, but it's a visualization which is mightier than ICANN map. In the exercise, we will use that in a hierarchical version, so you see how this really works out for you if you're using that on different levels of things. And last but not least, we have the complex and data and relations visualizations. Small disclaimer, we didn't talk about every visualization techniques of previous categories, and we certainly will not about every category in here, because it's collecting everything that's possible. Just an example, a word cloud would be a complex visualization technique. We can also, of course, draw networks and things like that, but a word cloud is the simplest form of that, where we can, for example, also display non-numerical data. For example, if you have a website with keywords, we can simply collect how often each word is used on a website, and the more often a word is used, the bigger it gets in our word cloud. And therefore we can simply display how often words are used, how important words are in here, which is something, for example, WordPress is using for their CMS, but it's also used in other contexts, but just an example for a complex visualization technique. Yeah, okay. That was a fast run through the complex visualization techniques. As I said, we will have more detailed introductions to those in the exercise, where you can use these techniques to gain insight into real data, which is far more useful than this fast run through. However, I want you to first get to know them before you're using them in the exercise. The last thing for the data lecture is data similarity and dissimilarity. And that's a very important thing, because we are using data similarity and dissimilarity a lot in the real methods. For example, clustering is based on similarity. We have to have some definition of data similarity to be able to do clustering. And also for classification and outlier analysis, we might use similarity methods. So in lecture 7, in lecture 8, in lecture 9, we will use these methods. I already talked about a cluster during scatter plots. So we can simply quickly define this. A cluster of data includes data objects that are similar to each other and yet dissimilar to data objects out of this thing. So we want to be similar to data objects within our cluster and we do not want to be similar to clusters outside of our cluster. But that's something we will repeat in the clustering lecture as well. For this, we first have to define similarity and dissimilarity. Similarity is, for numerical measures, how alike data objects are. If the value is higher, the similarity value is higher, the more alike the two objects are. In most cases, similarity is defined between 0 and 1. So 0% and 100% similarity. A 100% similar object would be identical, basically. While a 0% similar object would, of course, be totally other object. For dissimilarity, we do not have a percent range. Dissimilarity is most often without upper limits. A dissimilarity measure is most often also defined. Distance is, for example, a dissimilarity measure. So if we are taking a look at two cities, for example, or two locations, then distance is pretty easy to comprehend. And of course, there's no upper limit to distance between two locations. On Earth, it might be, but if we are going into space, then there's no upper limit for distance. And that's why we do not have any upper limit for dissimilarity, but we have an upper limit for similarity, because there we can not be more similar than 100% similar. If we are talking about something like proximity, and that's something I will avoid due to that, we can either talk about similarity or dissimilarity. So it's not that well defined. So avoid using proximity. If we are talking about similarity, we also have to talk about dissimilarity matrices. And to be able to talk about dissimilarity matrices, we first, of course, have to talk about data matrices. I hope most of you already know what a matrix is. Is there anyone in here who doesn't know about matrices? Okay. Then I skip the definition of matrices and simply go to the more precise, more important definition of a dissimilarity matrix. A dissimilarity matrix is simply comparing multiple data objects against each other. Again, let's say we have data object 1, data object 2, data object 3, and we want to compare these similarity or dissimilarity wise. Then we would do basically the same thing we have done with a scatterplot matrix, and we are comparing first the similarity of D1 against D2, D1 against D3, then D2 against D1, and so on. In most cases, since the similarity is symmetrical, we would leave out everything above the diagonal axis, so we would skip that. And we are only taking a look at the downside, or at the lower comparisons. That's why we have zeros up here, because we are not comparing the upper bound, we are just comparing on the lower end of a matrix. If we are using, if we are doing a similarity matrix, which is also possible, we would define most often similarity as similarity is 1 minus the distance of the thing weighted. So we have to take a look at the highest and lowest dissimilarity to be able to be in this definition of 0 to 1. Now let's get to similarity measures. Similarity measures, of course, exist for both things, for nominal data and numerical data. For nominal data, there are some general methods which can be used for every kind of nominal data. It might not be the best, because there might be some aspects that are more important, there are some aspects that might be less important between nominal attributes, of course. The most simple method to compare two nominal tuples against each other is a simple matching coefficient. So let's say we have persons with hobbies and with whatever. Not a good example, but a car model. Whatever. So if a person has a hobby tennis and a car model BMW, and a second person has the hobby tennis as well and a car model Mercedes, then the simple matching coefficient would simply take a look at every matching attribute and every not matching attribute. And therefore, the simple matching coefficient of this would be 50% in this case. Because the two persons have one matching attribute and one not matching attribute. Pretty simple to do. However, as I said, there might be certain weights to attributes to really comprehend that. I would say if you're talking about similarities in friendships, then I would argue that hobbies are far more important than the model of a car. So we have different weights in here. So a simple comparison might not be the best for your use case. The next thing is one-hot encoding. One-hot encoding becomes relevant for other methods as well, not only for comparison. It also becomes important for, for example, frequent pattern analysis, the methods of frequent pattern analysis. One-hot encoding, I think I have already introduced in one of the past lectures. Maybe I'm wrong with that. But let's say we have a person 1 and a person 2. And we are also talking about hobbies, okay? Person 1 has hobbies tennis and skiing. And person 2 has the hobby tennis and clubbing. Then a one-hot encoded version of this would take a look at every possible hobby, so every hobby that is present in our dataset, and that would create one specific attribute for that. So we have one attribute tennis, one attribute skiing, and one attribute clubbing, because we have these 3 different attributes. And then we would simply take a look at every entry, data entry, and simply one-hot encode it. So we would put a binary value to is present or is not present. Since person 1 is playing tennis, we put a 1. They are also skiing, but they aren't clubbing. And then tennis 0, 1. That's one-hot encoding. And using this, we can, for example, also use the simple matching coefficient, but we can also use more sophisticated comparisons more easily. For example, transactional databases. For values which have a meaningful order, for nominal attributes, we can also use integer encoding, where we simply put a value, a numerical value, to each of the things, and therefore we end up with a numerical value for ordinal attributes. But that's of course only possible if we have ordinal attributes, so we have a meaningful order in the nominal attributes. For binary attributes, so for example, we can use that for one-hot encoded data as well. We can also use the so-called Jacquard coefficient, which is something to also display proximity. Proximity is, again, too general. Since we are talking about 1 minus distance, we are talking about similarity in this case. For the Jacquard index, we simply have to take a look at a contingency table. And so that's something we also might or will reuse in a lot of chapters. A contingency table is simply a table where we count how often the 2 data objects we are comparing both have a 1. So Q in here, for our example down here, and I will erase that for avoiding confusion, would be 1, because we have one case where both are 1. R would be, and let's say we have A up here and B down here. So the y-axis is B, the x-axis is is A. R would be 1 time. S would be 1 time. t would be 0. And that's the contingency table, because we can then simply use these formulas to complete the other cases. And now we can compute, the Jaccard index by using Q, so 1 in our case, divided through Q plus R plus S, which is all are 1, so we end up with 1 divided through 3, and we end up with 1/3 of similarity in our case. And that's the Jaccard index. We can also do that for more sophisticated data sets, of course. For example, if we take a look at this data set, where we have 3 data entries, we can also calculate 3 different distances in here. That's something you can do at home to test whether you have understood the Jaccard index. I hope the little example down here was enough to comprehend the general workings of that. Now we can test that at home because of time. Okay? So that's about non-numerical data. Now we can get to numerical data. For numerical data, the problem is that if we are comparing 2 different attributes, those attributes might have hugely different scalings. So we might have an attribute age and an attribute income. Age is typically between 0 and 100. Income hopefully is not between 0 and 100, but is more or less between 0 and 1 million, whatever. So we have a hugely different scale in here. If we now use some of the comparison functions we are introducing later, then these 2 attributes would have hugely different influence into our distance. The income would be far more important than the age. And due to that, we have to normalize or even standardize data. If I remember correctly, we will get to normalization in general in the next chapter, and not in this chapter. But one specific normalization function is the standardization, the Z-score normalization. And that's done by using the standard deviation, the mean, and the value of the thing. It's used to have the same standard deviation for every attribute. And that's where Z-score normalization is good, or standardization is good. You should apply some kind of normalization before applying a comparison of numerical values. I will get into more detail on Z-score normalization and other normalization techniques in the next chapter, so I will leave it here, but you should remember to first normalize and then compare numerical values. Basically, distance on numerical data is most often done via this formula. This formula is the so-called LN norm, where we use a certain value h to define different distances. Let's first take a look at 2 specific h's. With h1, we end up with the Manhattan distance. So we put in this general formula h to 1, so we remove the root, and we also remove the square in here. And we end up with a formula like this, where we compare two different data objects against each other, and for each attribute of the two data objects, we simply subtract the value of the one data object of the other. So let's use this example. Okay? Let's use data object A, or data object 1, data object 2. In this case, we would simply take a look at 1 minus 2 plus 1 minus 3 plus 1 minus 4. And that's basically 1 plus 2 plus 3, so is 6. That's the Manhattan distance. The Manhattan distance is pretty easy to comprehend, the name Manhattan distance is pretty easy to comprehend if we take a look at a two-dimensional example. Let's say we have the two dimensions A and B, and we have a data point here, and we have a data point here. In the Manhattan distance, we would not compare the straight distance between the two, but rather we would take a look at this distance. So we would go around a city block. And that's why it's called Manhattan distance. Because we do not compare the straight line, but we have to go around a city block. And Manhattan is famously consistent of rectangular city blocks, so it's called Manhattan distance. And basically, that's how the Manhattan distance works. If we now go to the Euclidean distance, which is simply the same thing, we are putting a certain h value, specifically h2, into this formula, and use that. So for the first time, we have a squared root and a square in here. So we are replacing, or we are putting a squared root out of here, and then we are also squaring the difference in here. So in this case, we would have something like this here, 1 minus 2 squared plus 1 minus 3 squared plus 1 minus 4 squared, which is, in this case, 1, 4, 9. And the square root of 14 is something I can't do in my head, but it's square root of 14, the difference. Okay? This distance is now the straight line difference in a two-dimensional sense. So we are measuring the direct distance in here. We can also use other h's for L3 norm, L4 norm, whatever. Most often we are using either h1 or h2. One important thing is also the Lmax norm. However, you're using that in very specific cases, and most often it's not used, but it's certainly interesting to know about that. We can also try to get to h infinitive, but most often it's not done. So, and it's very complicated mathematically. But the Manhattan distance and the Euclidean distance are the two distances we will use a lot during the upcoming weeks. Okay? Summary, we talked about different data attribute types last week. We talked about different types of data sets last week. we talked about basically statistical descriptions, basic data visualizations, and also data similarity today. These steps are already the beginning of data preprocessing, which is the next chapter, and I will start with the next chapter because time right now. But are there any questions regarding this chapter? Okay. Then let's get to the next chapter, which is data preprocessing. And data preprocessing, we will talk about data cleaning, we will talk about data integration, data reduction, data transformation, and discretization, which are the most important preprocessing steps we have to perform. Why do we need that? Because data quality is very important for our later methods. We can take a look at data quality in different dimensions. For example, data might be accurate or it might not be. So whether data is correct or wrong is very important for us. If we are working with wrong data, non-accurate data, then our results, our patterns we read out of these data might be useless. We need as complete as possible data. If we are missing a lot of information and we have a lot of nulls in our data set, that's not good. We need consistent data. So data should be in the same format every time. We need time data, data that is timely updated, so it's as close to the present as possible. If we are doing analysis on temperature development and we only have temperature measurements from before 2000s, then we can't really derive something for these days. We need believable data because only then we can know how accurate the data is. And of course, we need data that can be understood. If we're taking a look at this data set, for example, we do not know what A is, what B is, what C is. We can't interpret this data. And that's something that is the case for a lot of real-world data sets, I can tell you. So a colleague of mine is working on Siemens data, Siemens Energy data, and he gets a lot of data sets where we have attributes with some numerical values in them, but they don't know which attribute is defining which sensor. And his research is on how to get back to a readable data, interpretable data. Based on these things, we have a lot of tasks in data preprocessing because we want to get as qualitative data as possible for our methods. That includes, for example, data cleaning, where we fill in missing values, we smooth out noisy data, we try to identify and remove outliers, resolve inconsistencies. All these things solve problems with data quality, or try to measure, get to measurably better data quality. We, of course, also have to integrate data. If you have multiple data sources, for example, multiple databases, we have to put them into one data source. We have to also take a look at data reduction, because the more data we have, the more dimensions we have, the harder it gets to work with the data. That includes dimensionality reduction, it also includes numericity reduction, and it also includes data compression, so my research field. And then we also have to talk about normalization. I already teased that in the standardization slide beforehand, and concept hierarchy generation. Let's start with data cleaning. Data in the real world is not very qualitative, and most often it's referred as not very clean, but dirty data. So dirty data is data that isn't fulfilling the different aspects of data quality. There are very much many kinds of dirty data. For example, we can have incomplete data, which isn't fulfilling the principle of completeness in data quality. We can have inconsistencies, errors, noise, outliers, and other things. For incomplete data, the example is pretty easy. We have a data set where simply we have some gaps. For example, we do not have the age for a specific student. Or we do not have the matriculation number for another student. That's incomplete data. And the reason for that might be that the data is not yet available because it's just entered in the system. There might be any kind of malfunction, or it's just a human error. And more often than not, it's just a human error. To solve these problems, we can, for example, just ignore the tuple. So we are removing the tuple from our training data set. We can try to fix the issue by, for example, talking to the experts and try to find the real value. In this case, we can, for example, try to look up whether matriculation number has a birth date in some other data set, so we can fix that. Or we can fill it out automatically with a global constant. In this case, that wouldn't be very helpful. We can, for example, use the mean. However, we risk that we are somewhat modifying our results, making them bad by filling out the age of this matriculation number with the mean. But sometimes it's feasible. In general, if we're filling out automatically, we try to find the most probable value. And that's most often more advanced than just using the mean or the mean of the class, which we will see in the exercises. For inconsistencies, we have to talk about, for example, different grading systems. In some universities, we might have numerical grades, just like at FEU, but in some other universities, for example, in Indian universities, I know about that, we have a lot of alphanumeric grading schemes, where we have A as the best grade, or American universities, for example, are using alphanumeric grading schemes as well. That's inconsistent. We have numerical grading and alphanumerical grading in the same column. The same is true in this column where we have Michael for one applicant and an applicant number for the other applicants. These things might and most often are resulting out of merging data from various sources, but they also might be missing conventions or human errors, of course. One good example for an inconsistency which very often happens as well is, for example, with genders. You can put F and M into your column, but you can also put female and male, or diverse, whatever, into your column. And this is very often the case in real-world data sets, that there is a missing convention, and therefore people put in their first thought on these things, and that's not working. These things can often be solved, can most often be solved with manual data cleaning, and they can very often also be solved via semi-automatic data cleaning. So if I know about, I've seen you in a second, let me finish the sentence. In many cases, we can just have a script in our hand which knows about the grading system of a certain Indian university and just transforms that into the German university scheme. Your question? No. So the question was whether data cleaning and preprocessing is the same thing. It's not the same thing. Data cleaning is a step in data preprocessing. It's a step of data preprocessing. But, sorry, German in here. It's a very important step of data preprocessing, but it's only one step in the whole pipeline of data preprocessing. Okay? Yeah. We will do that for some examples in the exercise as well. Then we can, of course, have errors, so problems with accuracy. These can, again, be done by human error. They can be transmission errors. They can also be malfunctions of any sensor, for example. If we're taking a look at this value in here, we know, or you should know, that KDD with exercises gives you 5 ECTS, so that's an obvious error. So, that's an obvious error in here. If you're an expert in the domain, you can simply correct that. You spot that error and you fix that. If you do not know, you do not recognize it's an error because FAU doesn't offer courses with 5 ECTS, with 6 ECTS, but you do not know the real solution to that, you can also ignore the toggle. So you can just skip it. For errors, it's very unlikely that you find a very 100% automated solution to fix in errors, because these errors are very often very case dependent. You have to have a lot of domain knowledge to really identify errors and also correct them. So it's nearly impossible that you find a general solution to fix errors automatically. In general, for a certain domain, it might be possible. If you have a certain domain where you can look up, for example, real values in other database, then errors are fixable automatically. One related problem is noise. Noise are small inaccuracies and inaccuracies, which can, for example, also be transmission errors or sensor inaccuracies and things like that. They very often occur with sensors, where we have small jumps. These things are very hard to spot. Most often, these noise problems are just avoided by using data smoothing before you applying any method. So if you have very specific double values and you do not need these specific values, it's always good to get rid of them beforehand to smooth them out a little bit. Which is something we will do later. Not today, but next week. Very important, errors and noise. An error is not always noise, but noise can be defined as a specific kind of error. So basically the same thing we have done with data cleaning and preprocessing. It's a subset, basically, in here. Very important, not every error is noise, but noise can be referred as a specific kind of error. And the last thing are outliers. Outliers are something we already talked about during the interquartile range slide, and we will talk about in a specific lecture. Outliers might indicate errors, but they might also be very rare events. Both things are possible. In most cases, you try to find outliers to either check whether it's an error which has to be fixed, or because a very rare event might be something very valuable to know about. If you know about a very high temperature outlier that might occur in a certain country, you might want to prepare for this specific case, if it happens again, for example. So outliers are very nice to know about because either they are indicate an error or they are a very nice event, rare event to know about. Yeah. If we know about these things, we can now talk about data cleaning as a process. Where we first, of course, have to find problems in our data. To find problems in our data, we can, for example, use metadata. So, for example, our quartiles, our outlier detection, are automated. We can check for certain rules in our data. We can have rule-based problem detection. And if we detect an error, then we can, or not an error, but a problem with the data quality, we can use specific sets or take a look at those problems manually. There are some commercial tools to find problems and to fix these problems. Those are either using data scrubbing, where simple domain knowledge is used to detect errors and apply corrections. For example, if you have a website where your customers are inputting their addresses, you can have other database backend where you simply check whether the zip code is matching the city. And if it's not fitting, then it's either fixed or disallowed at the point of input. That's data scrubbing. With data auditing, we try to analyze a huge data set, discover rules and relationships, and try to find violations against these newly found rules. For example, if we have correlation between two attributes and one or two values work totally against this correlation, then it's likely that these are problems. Both things are often used in commercial tools. After we have identified and probably fixed, we also have to talk about data migration, integration, of course. There are tools for that as well. And data integration, so this step is basically something we will talk about next week because we are at the end of our time today. Are there any more questions regarding today's lecture? Okay. One last thing. Since I know that not everybody got a slot in the exercises, this week we will take a look at the attendance in the exercise sessions. And if there is enough place in the exercise sessions, we will extend the number of students that are allowed to go into every exercise session. So keep an eye out to the exercise slots if you want to switch. Because it might be extended. For the Thursday and Friday exercise, this change probably only happens on Tuesday because I'm in holidays Thursday to Monday. but we will extend the sizes of the exercises based on the available slots, available space in the exercise room this week, just as a little reminder or a little information. Okay, have a nice week. See you again next week on Wednesday.